So we will continue our cache animation, and this time we're going to look at the set associative cache, right? So for this figure shows an example of two-way associative cache. Why two-way? Because you can see there are two columns of data. So the data array has two columns, so that indicates two-way associative. And because for each set we can keep two data blocks, that means we have to remember what they are. Therefore, the tag array also has two columns, one tag for each block. And you can see also there's like two comparison logics, one for each tag. And we have a multiplexer also to select which block that has a cache hit, basically. All right, so let's look at the example. So again, we have the same cache size, so 256 bytes, except that now we have a two-way set associative cache. The block size is the same. So now we need to complete the following sequence, find the content of the cache after each access. As usual, count number of hits, number of replacements, etc. All right, so let's first compute what is the size of each field. So in this case, we divide the size with block size and associativity to get the number of sets. So we have 256 bytes divided by 32 bytes block size and 2 associativity. So it comes down to 4. Okay. So we have 4 sets instead of 8 with the direct map cache. So the number of bits that we need is also fewer. In this case, we have 2 bits because log 2 of 4 is 2. The block of sets bits is still the same, which is 5. And the number of tag bits now has increased because we subtract 32 with 2 and 5, we get 25 bits. All right, so let's split the address again. So we start with a 32-bit address, which is 8 hexadecimal digits. We take out the last 7 digits, and then we show that in the third column. So we have index bits and offset bits. So now we only have 7 bits there. That means for the tag we only have 25 bits. That means we have 6 original hexadecimal digits, but then we also have the last one. Okay, so now you can see, for example, the tag changes because we have 25 bits. Okay, so and then the same as before, for convenience, we convert the index bits from binary to decimal just because it's more friendly to us. And finally, what we need to figure out is what happens to the cache. Do we have a cache? Do you have a miss or cache hit, or a miss with the replacement? Okay. So now in the animation, I'm no longer going to show you the data array. I'm going to show you just the tag array. Okay. So there are 2 tags per set, and we only have 4 sets. Let's start with the first access. In the first access, we have access to index 3. So we use that to index the cache and read out the tags from set 3. So both tags. And then it turns out we want to access tag 1FE0081. And when we perform the tag comparison, we have a mismatch. Okay, that means we have a cache miss. And we install the block in the first associativity, so in the first way, both in the data array and in the tag array. Next, we have an access to index 2. So we compare against tags in set 2, and we want to access 17DDE00, and they mismatch. So we have a cache miss, and we have to bring it from the cache, so from the memory. Next, we have access to index 3, and we read both tags out, but what we want to access is 002020. And in this case, they mismatch with both of them. So we have a cache miss, and we have to bring the block from the main memory, and we can install it in the second way, okay, because it's not occupied right now. Next, we have access to index 3, and we read both tags, and it turns out we want to access from tag 1FE0081. So in this case, we actually have a match with the first way. What happens next, which is not in the animation, is that we need to read the block from the data array of the first way and select the bytes to return to the processor. Okay, our next access is to index 3, and the tag is, so we read both tags, and the tag is 0002020. So by comparing them, we find that there is a match, but this time the match or the cache hit is on the second way, okay, which is that's going to be the block that will be read, so the second second way. Next access is to index 3, so we read them out again, and we want to access tag 00043007. And in this case, it turns out that we don't have the tags currently, so that means it's a cache miss. But notice that in this case, we have to replace one of them, right? We want to replace one of the blocks, and the decision that has to be made by the cache replacement policy. And in this case, if the replacement policy is LRU, we have to figure out which of the block is least recently used. And therefore, since the least recently used is the first on the first way, so we replace that block and replace it with a new block. And next we have access to block 3, to set 3. So we read out set 3, the both tags, and compare the tag. And in this case, we have a cache hit. All right, so basically this is the end of the animation. You can see that the difference between direct map and set associative cache is that in a set associative cache, you have more tag comparisons. So depending on the number of associativity, you have to kind of compare multiple tags at once. Now this is performed in hardware, so it's performed in parallel. So the cost to you is basically power consumption rather than latency. The second difference is that since when we have a cache miss and we need to replace a block, since we have more than one choice, we have to employ a replacement policy, which in this case we assume to be least recently used, but there are some variations of that implemented in a real processor. Okay, that wraps up our cache animation. Thank you.